Well, welcome everybody to the Third Act Advocates for New York State Climate Policies. My name's Maggie Riley. I'm from Third Act Upstate New York, and I co-convene this with Catherine Alford from Third Act New York City. And we're glad to have Dr. Richard Perez today for speaking. And he's going to talk to us about the big energy picture. Is 100% renewables achievable? He's going to spotlight New York State and discuss the implications for land use and the impact on farms.
Thank you. Can everybody hear me well?
Yes. Yes.
Okay. So I'd like to tell you about solar energy and the New York power grid. First, I will go into the big picture, showing that solar is a vast resource, that it's inexpensive, that it's scaling up rapidly around the world, that it can be a firm power resource available 24 hours a day, 365 days a year, wherever you are, and that it opens the door to 100% renewables that can be affordable. Then we'll focus on New York State and ask the question, where can we deploy all the solar that would be needed in a 100% solution? What are the impacts on land use, especially agriculture? And finally, let's open the door to see how it could unfold. How can it happen? Even if it looks good, it's nowhere sure that it will be happening. There are hurdles, but there are also solutions to those hurdles. So let's dive into the big picture. That's our fusion reactor. And as you will see throughout the talk, I like numbers. Numbers generally hard to fake numbers, to go around them. So we have a giant source of power, 3.8, 10 to the power 26 watts. Every square meter of the surface of the sun is 63 megawatts. So it's highly powerful. By the time it reaches us on planet Earth, it dissipates quite a bit because of the huge space around the sphere that is covered by the Earth radius. But it's still over 1,000 watts per square meter just outside the atmosphere. At the surface, because the Earth is a sphere and only receives power on the sun-facing side, and because of clouds and the atmosphere, we get only 170 watts per square meter on average. That's what we call solar irradiance. For information, that's how it's distributed in the US. In upstate New York, we're at about 150, slightly below the Earth average. The highest point in the US is Yuma, Arizona, 240. And you'll notice most people think it's 10 times more in the Southwest and in New York, but it's not. The difference is not huge. So we still get quite a bit of sunshine here. That's how it's distributed around the world. The sunniest spot on the planet is the Atacama Desert in Chile. And the gloomier spot, the less sun, is in northern Siberia. So 170 doesn't sound like much, but if you add it up for the entire planet, it's a big number in terms of energy. It's 77,000 terawatt-year per year. And that unit of energy that I will refer to in the next few slides, 1 terawatt-year, is almost 9 trillion kilowatt hours. So it's a big unit of energy. And let me represent that unit of energy by that sphere here. That sphere represents 77,000 terawatt-year. And when I compare that to what we use on the planet in terms of energy, you can see that there is plenty to go about. This is 21, that's what we use. That includes transportation, industry, the AI development, everything. So you can see there is room to grow. Solar resource is certainly much bigger than our finite resources, which are powering the world economy today. Even uranium, people are talking about nuclear. Petroleum is dwindling fast, natural gas as well. Even coal is limited, and that's once and for all. Those resources are finite, whether with a solar resource, you get that every single year, a big sphere like that. It's also much bigger than all the other renewable combined, many of which are, in fact, byproduct of solar resource. They are second order, like wind is created by solar energy, that differential heating creates the wind, and the wind creates the waves. And you can see when you go from first to second to third order, you lose quite a bit in the process. Biomass, which is touted by many as big resource, is in fact quite small, and includes the entire, if we converted everything that grows into energy. Hydro is quite limited because there are only so many rivers that you could dam. The only two that are not solar byproducts are geothermal and tide. Tide is minuscule. I call it moon power. And geothermal, given current technology, is quite small. If we can master deep well geothermal, drill down to 20 or so kilometers down and do it economically, that's potentially also a big resource, but it will not be quite as big as the solar resource. And the instruments that we can tap to transform that solar resource into usable energy by far is PV technology. State-of-the-art modules can convert about 25% of the sunlight into electricity today. When I was a student, it was 8, 9%. And we can expect that 10 years from now, it's going to be 35% with the advent of multi-junction, perovskite, silicon modules. So you can agree that it's a vast resource, and that's also an inexpensive resource. This is the history of price per watt of a PV module since the mid-70s to today. Today, it's just about a quarter a watt, and it's not going back up. Yeah, you may have tariff wars in the short term and everything, but fluctuations, the technology is getting better, cheaper, uses less material. So it's going to cost less than that in the future. Maybe not next year, but certainly 10 years from now. And it's already quite cheap. That's one of my favorite graphs that I like to vision. It comes from the Lazard Bank, and every year they compare the unsubsidized cost of energy production from all the resources capable of making electricity. And the two cheapest ones are solar PV utility scale and wind, onshore wind. People are talking a lot about nuclear, putting new nuclear plant on the way, but each time I hear that, that graph comes to mind, and it's quite a bit more expensive. First, it takes a very long time to build. At the end of the day, you're talking something that's almost 10 times more expensive than solar and wind. Although this graph, this is intermittent, this is not. So, but I'll come back to that in a big way. And if anything, that cost is going to go down because technology is getting better. And this one is probably likely to go up because of environmental concerns and geopolitical concerns, particularly natural gas. As we've seen in the Ukraine war in Europe, the prices went 3, 4 times higher for electricity generated from gas. So it is quite inexpensive today, and it's also scaling really fast. These are the installations of PV around the world since I was a grad student, and it looks like an exponential. And in fact, the best way to look at an exponential is to change the y-axis to a log scale, and that gives you the rate of growth. And it's been doing almost 30% a year, every single year, rain or shine, whatever happens in the world, crisis or boom, it's very solid growth. And interestingly, if you say, let's keep that 30% growth, do the mental exercise, you see that 15 years from now, there'll be enough PV on the ground to power everything on the planet. I'm not guaranteeing that it will happen, but just working at the numbers, it looks that way. And it's certainly doable because the manufacturing capability of PV is already much bigger than the demand. These are all the what the factories of the world can churn in terms of PV, about 3, 4 times demand already. So things look good in that realm. We are less aware of that in the US, but the world is certainly taking notice. So we have a vast and inexpensive resource that's scaling fast. But what about intermittency and 24/7 availability? So that's always you hear what happens during cloudy conditions at night for wind when the wind doesn't blow. This is always presented as a showstopper for the renewables, the wind and solar. But that's exactly what I'm researching. I lead the team at the International Energy Agency in the PV power supply group, which is focused on firm power generation. So if you look at it firsthand, this is 1 year of PV generation in a plant somewhere in upstate New York. So you can see it's highly variable from day to day. These are hourly data. This is the mean. It's summer peaking. If I look at wind generation, it's even more noisy. It happens to be winter peaking, but it's highly variable and it doesn't look anything like the load we're trying to serve. That's the load of New York City here. So at first look, it looks like it's never going to work. But as always, there are creative solutions that can work really well. So let's focus on a few days of the load here. So that's the regional load. And traditionally, the way to provide that electricity load is to have base load. In New York, we have Niagara Falls, we have the Canadian one near Montreal. We have big nuclear plants that provide your base load, and everything else is more or less natural gas that you can drive like a car. When with higher demand, you put more gas and then you throttle it out. And when you put run-of-the-weather resources on the grid at the margin, and here I have my VREs, variable renewable energy, solar and wind, and that's the way they're being deployed. I mean, my net metered system on my home, and I heard a few of you telling about your PV system. That's what they are. They're run-of-the-weather. They will operate at the margin, and that's what they do to the load. And when you have little penetration, it's pretty good. You have some peak shaving, everything looks great. But as you put more on the grid, you can see the emergence of a little problem here. First, dispatchable load underneath gets harder to manage. It's more unpredictable. And here I'm at 30%. I'm already denting into the base load, which cannot be managed. I'm only at 50%, and I have something that looks pretty ugly on my end. And I feel for the grid operators because when they question solar, that's what they see. And that's at the root of the negative market price you can see in some markets, the curtailments imposed and the moratorium that they want to impose on PV and wind deployments, all those growing interconnection queues, which are cited by the industry as takes 2 years to connect, they trace their problem to the fact that we are trying to fit a square peg in a round hole. And that's also at the base of the tug of war between the grid operators and the renewable industry. They don't talk the same language. So we have that big growing problem. And most people say it will take a super grid to change it. You're going to need to bring the wind from the central Great Plains and the sun from the southwest and even everything out, even the weather out. At the IEA, what we envision is a firm power solution. So you actually transform at the source that run-of-the-weather signal into something that looks exactly like the load you're trying to serve. And when you do that, the penetration can be seamless. You can seamlessly displace the gas market that you ultimately want to displace. And that can happen locally without a major grid buildup. So how do you do that? There are 4 things to do. First, You have to blend the wind and solar optimally, and that optimum varies as a function of your location and the shape of the load. You, of course, add storage, and storage constitutes the short-term glue of the system to take care of any short-term variability fluctuations of the solar and wind. So you need that as in the system, but you also need something that's totally outside of the box currently. It's called implicit storage. You build more solar and wind than needed, and then you curtail the excess. You apparently waste the excess, but that's the way it works. So this is that axis here represent the cost of electricity. So we know that from the Lazard Bank I showed earlier that run of the weather, wind and solar are very, very cheap. But if you are to firm that, make it 24/365 only with storage, and that's the route we're engaged now, it's going to cost a fortune. So it's a non-starter proposition, and often the thinking stops there. But there is a workable proposition which is totally counterintuitive. If you overbuild and by design curtail, like throw away, apparently waste some of the resource, you can reduce the requirement of storage to the point where you have a solution that makes sense economically. And that part of PV, the green part here that's not being used, that's being apparently wasted, we call that implicit storage because it acts as a catalyst to storage. And the last leg is to add flexibility to the system to make the loads seen by the PV and wind look more like the supply. That can happen on the demand side, but effectively that can happen on a much grander scale on the supply side by keeping some of the dispatchable generation using well-known technology, gas turbine, but operating them with clean fuels, e-fuels. And if you're not familiar with e-fuels, that's something that's really up and coming. It's a new commodity that's made purely from wind and solar, producing hydrogen, but you're not using the hydrogen, no hydrogen economy needed. It's converted with biogenic carbon and oxygen into any type of fuel that's currently used. So that's the way we're going to power the boats and fly the planes with super clean fuels. You can make e-methane. The only issue is that it's very expensive, but even very expensive, and it's going to be produced just like other commodities where it makes sense to be produced. So central, southwest US, North Africa, all the regions where you have lots of wind and lots of PV. But when you put all those elements together, you can come up with a solution that looks very promising. As part of the IEA team, I have experts from several countries, and this is what we can expect for 24/365 cost of power generation around the world. And it's well in line with the wholesale costs we see today. For instance, on NISO, year to year, it can be 5 to 7 cents per kilowatt hour. So we can do the 100% renewable at that price. And let me illustrate that with a study we just completed for climate, which is not very different from New York. It's Nova Scotia. We did that for Natural Resource Canada. And they wanted to know if they could not only do 100% renewable, but if we could do that if we fully electrified the load with transportation and building. So it's a whole electric province. Can we do the job with PV and wind? The horizon is 2050. So our first exercise was to model the future load, and you can see it's much higher, 80% higher, and it's also much more variable because of electric transportation. So we have that load, we have the wind supply, we have the solar supply. We use for future price what the projection from NREL. We also have batteries with the same projection, future batteries at $40 per kilowatt and $65 per kilowatt hour. We have a supply side flexibility, brand new gas turbines, but operated with e-fuels which are about 5 times the price of natural gas. In that case, natural gas would be about 2 cents, 2 to 3 cents OPEX. E-fuel is 18 cents OPEX. We have a little bit of run-of-the-river hydro in the province that we're going to keep. And of course, we have that implicit storage. And then we run a simulation of the Nova Scotia grid. So we have our PV and wind, which are our main workhorse for the generation, trying to meet that load. And the dispatch algorithm looks complex, but it's fairly simple. If the PV and wind is less than the load, then you fully dispatch it and you use storage and e-fuel for the rest. If it's bigger than the load, which happens very often, first thing you will charge storage. And if it's full, then you will apply implicit storage, which is a nicer way to say just waste it apparently. But when you do that, it looks pretty good. That's the sweet spot for Nova Scotia. In terms of energy contribution, it will be dominated by wind. There are fantastic winds there, but still quite a big chunk of PV. You will see the expensive e-fuel only occupies 5%, and the run-of-the-river hydro is the other 5%. In terms of capacity here, wind dominates, but PV is not far behind. Wind has a much higher capacity factor. Only 5 hours of battery is needed, not days of battery storage. 5 hours of load. And the bottom line is 4.5 cents per kilowatt hour LCOE. Contrast that to the current cost in Nova Scotia of generating, it's about 9 cents per kilowatt hour. So the future looks pretty good for them. Importantly, we need to waste apparently 20% of the PV and wind output. Because if we don't do that, this is how much it would cost. So that's highly counterintuitive, but it really works. One thing that I would like to point out to you is that e-fuel, even though it's a tiny fraction, in terms of capacity, e-fuels are capable of meeting all the demand at any point in time. So it's an insurance against anything, any prolonged periods without PV or without wind. It's there in the system. And I had a good discussion with NISO about it, and they liked it a lot because they're trying currently to build more gas generation. And I'm fine with that as long as you plan to convert it as soon as you build your big 100% renewable into something that will use the more expensive kind of fuel. And that can happen, just fuel switch, no change in technology needed. And if we do that, the future looks pretty good. One thing in the way of that is that it's not doable under current conditions. The current market rules that cannot happen. You need to change the way the markets operate because today curtailment is perceived as a loss. So every power producer is trying to maximize output. And there is no provision to optimally deploy all those solutions and to operate them in real time to deliver a load shape. You need aggregators and virtual power plant operators to make this happen. And this current market, that cannot happen. We have a day-ahead market that's based on energy, where everybody bids on energy and not availability. So one of the things we're looking at in the IEA is how can we change that paradigm? And I think an effective solution would be to keep the existing market for the dispatchable resources that we have on the grid today. So no change there. You keep the day-ahead market and the people bidding on it. You keep the long-term forward market for the baseload power. That's what we have now. And you operate a separate market for all the renewables, the variable renewables. And that market is not addressed to the producers, but to the aggregators of everything underneath them, wind, solar, battery, and flexible generation. And that includes everything connected to the grid. That would include my solar system and your solar system. If you really want it to happen, that's the way it has to work. And that would not be energy-based, auction-based. It would certainly be capacity based. So what the aggregators will guarantee is to deploy at any point in time the right amount to meet the load and not count the kilowatt hours as we do today. And if you want to know more about it, just published a major milestone with the International Energy Agency called Firm Power Generation. It's just out of press 2 weeks ago. It includes 40 authors from 10 different countries. And it's a bit technical, but interesting. So we have a vast resource, inexpensive, that's scaling very fast, and that can be available 24/7, 365.